Now we will discuss random variables on the same probability space. We have said that we can define multiple random variables on the same probability space. They may have same CDF or may have different CDFs. So let us take a few examples on that. The first example would be a person arriving between 2 to 3 p.m. So your sample space will be 0 to 1, where any outcome represents the hour that has spent before the person has arrived. And sigma algebra would be a Borel algebra on that. And here for probability, we'll use a Lebesgue measure. Now we will define another random variable. So one random variable is x omega equal to omega. So we have seen this case in the previous discussions. Now we will define one more random variable, which is z omega equal to omega square. So this is how we map from omega to z. So what will be the CDF of this z omega? So recall that CDF, which is fz of z, is nothing but the probability of the pre-image of a set of B, where B is equal to minus infinity to z. So what we do is, for any z, we take this B, which is from minus infinity to z, we compute the pre-image of this set under z, and then we compute the probability of that pre-image. That will be the probability law of z of B, and that will be same as CDF of z at small z. So if z is less than 0, then B would be minus infinity to z, and this will not contain anything between 0 to 1. Now, if you look at the pre-image is given as by all omega, such that j omega is in B. So what is z omega? Omega square. So z omega is in B means z omega is less than small z, less than or equal to small z. And if z omega is omega square, what will it be? So this will be omega is equal to omega square is less than or equal to z. So when I say z is less than 0, this means omega square should be less than or equal to z, and z is a negative number. So what are the omegas such that omega square is less than a negative number? There are no omegas. So the set will be empty, and the probability of that empty set will be 0. Now if I take z equal to 0, then this pre-image will be made from all omega such that omega square is less than or equal to 0. And that will only contain omega equal to 0. So the probability of single set is 0. Now if I take z between 0 to 1, then this will be omega such that omega square is less than or equal to z. So this is equal to omega is less than or equal to root z. Now this is what are the omegas such that omega is less than root z? Since omega can be only between 0 to 1, and root z is of course less than 1. So and this is also less than z. Yeah, sorry, root z, and that is less than 1. So omega less than equal to root z, and omega need to be greater than 0, and root z is less than 1. So taking these three conditions, this set will be equal to a closed set from 0 to root z. So probability of this set will be root z from Lebesgue measure. And if z is greater than or equal to 1, then omega square less than z will contain all omega, all capital omega. So this will be the complete set 0 to 1, and probability will be 1. So you said that I have computed CDF when z is less than 0, the probability CDF is 0. From 0 to 1, it increases with as root z, and then at more than 1, it becomes constant as 1. So it is possible to define many such random variables on the same probability space. I'll give you some example of that. So x omega equal to omega is the first one. Then we talked about z omega equal to omega square. And then we also have seen y omega is equal to 1 minus omega. These are three random variables. They are all mad from omega. And you can see that sometimes we can also represent them in terms of each other. For example, x omega is omega and y omega is 1 minus omega. So we can also say that y omega is equal to 1 minus x omega, or x omega is equal to 1 minus y omega. Similarly, z omega is nothing but x omega square, and x omega is square root of z omega. Y omega is 1 minus square root of z omega. And because all x, y, z are always positive, we don't have to worry about the negative square root or positive square root. They are only the positive square root here. But when they are, we have to also take care of those. So the interesting thing is, if I am interested in knowing the CDF of y, we will later on see that it is possible, because y can be written in terms of x. It is possible to calculate the CDF of y directly from the CDF of x without knowing the underlying probability measure or sample space. So sometimes you will see that people will omit the information about sample space and directly work with the random variables. In that case, y omega is equal to 1 minus x omega is written as y equal to 1 minus x. Similarly, z equal to x omega square is generally in shortcut can be written as z equal to x square. It means same thing, that for any omega, z is x square. But we can also see that it's possible to compute the CDF of z directly from the CDF of x without knowing the exact probability measure from which x and z are calculated. Of course, if I know the probability measure, I can also directly calculate z by knowing the relation between z and omega and capital omega. So we have seen that we can define multiple random variables on the same probability space. So the example which we can take here is, suppose the sample space is from 0 to 1, and the three random variables are defined in the following way: x omega is equal to omega, y omega is 1 minus omega, and z omega equal to omega. You can see that all three are continuous random variables, and their range is also 0 to 1. You can actually verify that they also have the same CDF. So it's easy to guess that x and z will have the same CDF, but we have also covered this in the past that y omega will also have the same distribution. Here we have taken the probability measure as the uniform measure or the Lebesgue measure. Now we also talked about that sometimes we can directly represent the random variables as a function of other random variables. So here y is equal to 1 minus x and z equal to x. From this it is more clear that z is actually equal to x and y is not equal to x. So we remember again, the equality means the function equality. So for two random variables a function. So for two random variables to be exactly equal, they need to be equal for every value of omega. So now we can see that we have defined two different random variables having the same CDF, which are x and y, and there are of course two equal random variables also which have the same CDF. So we don't have the knowledge about the definition of two random variables. Suppose then just by looking at their CDF, we cannot know the relation between them. We cannot even know whether they are equal or not. So we see that if the distribution of x and y are given to us and they are equal, we cannot tell whether x is equal to y or x is not equal to y. So how do we determine the relation between two random variables? Of course, if we know their exact definition, then it's much more clear. But suppose we can only know the distribution. So one way to know what is the relation between two random variables, we need to look at their joint distribution. Means, see, a distribution tells with what probability a random variable takes for which value. And here joint distribution we talk about that two random variables or more than two random variables how they jointly take probability, jointly take values. So let us see this. Let x and y are two random variables on the same probability space omega f p. Then you can see that if this is any value, so if x also takes value in a real line and y also takes a value in the real line, so you can basically see that if this is a 2D plane, then if you take any point xy and then you compute the pre-image of that in the original omega sample space, then you will see that this xy maps to a event, a outcome. Right, single value maps to an outcome, and any set or even if a singleton set maps to an event, an event. So xy maps to a event omega or outcome omega such that x omega is equal to this x and y omega is y. So so in other word, you can understand that this random variable x maps this omega to this coordinate x. Okay, but there is no condition on y, so it can be anywhere on this line. Similarly, y omega maps this omega to a y position, so it can be anywhere. And both values, if I know both x and y, if I map x and omega both, then I know they map to a point on this 2D plane. Similarly, if you take any set A, which is made from many xy points, and these xy are actually mapped to one outcome. So if I take this complete set, this will map to an event in the sample space. So this is the joint pre-image. So if I just want to compute for one x, you just care about only those omegas which maps to this x. But if you're talking about joint, then you have to calculate all omega which map to all points x comma y in this set. So their x should also be between these two boundaries and y should also be between these two boundaries. Only those omega will be the pre-image of that. So joint probability law of x and y is defined as which we say is probability on xy, probability law of xy of any set A. And now here A is a set of 2D planes. It's a Borel set on R cross R square. So probability law of any set A is such that it is a probability of the set of all omegas which are such that the x omega and y omega, their map under xy. So this will be a pair. This pair or point should be lie in A. So A is a 2D set like this, and all the omegas such that their map to which is a 2D point lies inside this A. That is the probability of that will be the probability of it. Okay, or in other words, this is, you can see, is a pre-image. Is a pre-image of A because this is made from all omega which maps to this set. If A is a 2D plane, so A can of course be written as Cartesian product of two intervals, 1D intervals. So if this is B, and this is C, then this black is called B cross C. Okay, because it is made from taking points from B as x coordinate and C as y coordinate. Okay, so if this A is written as B cross C, then we can also write the same formula in the following way, that Pxy of B cross C is equal to probability of all of those omega such that x omega maps to B and y omega maps to C. And B and C are both some Borel sets. Okay, so this map is very important here. Just understand that each point maps to each outcome maps to a point, and if you take multiple outcomes to form an event, they also map to a set here, a set of points here. And for pre-image, if I have to calculate the pre-image of that, you take all points in this set find who they do map to in the original sample space, and collect all those. That will be your event. So what will be the joint CDF? So this is the joint probability, and the joint CDF, as you remember, for CDF we take a specific set. So for B we'll take minus infinity comma x, and for C we'll take minus infinity comma y. So CDF of joint CDF of x comma y at x comma y is called is equal to probability of all omega, such that x omega belongs to minus 50 comma x, which other way means that x omega is less than or equal to small x, and then y omega is less than or equal to small y. So probability of this would be the joint CDF of xy. Okay, and just notice, if you denote EXY as the pre-image of this set, then the CDF is just the probability of this pre-image set. And just notice that this x comma y denote there are two random variables, and then this x comma y is this one is just the local variable. So you will change this x and y from minus infinity to plus infinity, and you will get the value of CDF at different points. And this xy denote the what random variables you are looking at. So if you change the random variable also, the complete CDF will change. See how we can compute the joint distribution by calculating this particular example. So let us see, take an example of flipping of two coin tosses. So flipping of two coins. So the sample space will be HS, TH, ST, and TT. So HS denotes that both coins are head, TH is first is tail, second is head. And now I define two random variables, x omega and y omega. X omega is 1 if outcome is HH or ST, and 0 if the outcome is TH or TT. So you can understand that this denotes 1 if first coin is head, and 0 if first coin is tail, regardless of what is happening with the second coin. And y omega is such that it is 1 if the outcome is HSTH, which means the second coin is head, and 0 if the second coin is tail. So we need to compute the joint distribution of this. So we have to take all the values of x and y possible in the 2D plane and first calculate the pre-image EXY, which is a set of all omega such that x omega is less than small x and y omega is less than small y. So if x and y, small x and y, both are less than 0, then what are the x omega which are less than this value x? There are no there are no omegas which maps to a negative number. So the set would be just empty set. Similarly, if I take x between, and that is regardless of what is the value of y. So only thing that if small x is less than 0, then that set will be empty. Similarly, if small y is less than 0, and regardless of what is the value of small x, the set pre-image will be 0, 5. So now let's take x and y both between 0 to 1. And then I ask you, what are the omega such that x omega maps to minus infinity comma x. So you can look at from minus infinity comma x, since x is more than 0 and less than 1. This means this set of minus infinity comma x only contains 0. Right, the rest value x omega cannot take. So we don't worry about that. So only value which is the range of x is 0. Similarly for y also, 0 is the only value which is in minus 20 comma y, which y omega can take. So the pre-image would be made from all omega which maps to 0, which map under x and map to 0 under y. So you can see that TH and TT maps to 0 under x, and st and tt maps to 0 under y. So what are the outcomes? Such that x omega is also 0 and y omega is also 0. The answer is tt. So this will be the free image. Similarly, if you take x more than 1 and y between 0 to 1, this means x minus 20 comma small x has both values 0 and 1, and y minus 20 comma y only has value 0. So in that case, what are the omegas? Says that x omega maps to 0 or 1 and y omega maps to 0. The answer will be st comma tt. Similarly, you can change y more than 1 and x between 0 to 1, and you get th and tt as a pre-image. And if x and y are both more than 1, then x omega and y omega both can take 0 and 1. So in that case, the pre-image will be just the complete sample space, capital omega. So once I know this, and suppose the probability measure is such that probability of HS is P1, probability of ST is P2, probability of TH is P3, and probability is P4, then depending on the condition, we know the probability of this set is P4. The probability of this set, ST and TT, is this plus this. HH and TT. ST and TT. So ST and TT is this P2 plus P4. Similarly, for this set, this will be TH plus TT. So this plus this P3 plus P4. So if you write this in terms of its function, this will be if x and y are both, one of them is less than 0, it is 0. If they are both between 0 to 1, then it's P4. If x is more than 1, but y is less than 0, between 0 to 1, then it's P2 plus P4. Similarly, for y is P3 plus P4, and if they are both, this greater than 1. If you plot this, this will look like a staircase in both directions. So if you move in this direction, this is as just at this point, you suddenly add y equal to 0, and then you suddenly add the probability corresponding to y equal to 1. Okay, and because you are moving in this direction, both 0 and 1 are included before it, so probability of 0 and 1 are corresponding to omega, so that x omega is 0 to 1 is already included. If I move from this direction, 1 is not included in x, so probability this I will add the x is 0 and y is also 0, and then x is 0 and y is equal to 1. Similarly, as you move from here or here. Now let us talk. Similarly, you can compute the continuous random variable joint distribution also. You have to just compute the pre-image carefully, and then they will map to some omega. And if you know the probability measure on original omega, you can compute this. So there is only one sample space, remember. So there is only one probability measure on omega, and every two-dimensional plane will map to the sample space. So if sample space is one-dimensional, you get a one-dimensional pre-image. Now, what are the properties of it? First of all, if x and y both moves to infinity, CDF would be 1. Okay, and this is very easy to see because as you move x and y to both infinity, the omega says that x omega is less than x and y basically covers all the possible outcomes because x and y omega both can only take a value less than infinity. So to prove it formally, we will apply the similar method. We construct a sequence, it's a two-dimensional sequence of x and y n such that both number moves to infinity as n goes to infinity. Now let's construct a en, which is a pre-image of set minus infinity comma xn cross minus infinity comma yn. So this is the set of all omega such that x omega is less than small xn, y omega is less than yn. So if I take limit x tends to infinity, y tends to infinity, and then if you look at this CDF, this is nothing but the probability of the probability that x is less than x and y less than y. Okay, and this is equal to limit n tends to infinity fxy xn comma yn because both x and yn goes to infinity. Now limit n tends to infinity, this will be nothing but probability of omega less than x omega is less than equal to xn and y omega is less than equal to y. Now this is nothing but the finite intersection of all Ens. Remember, as you yeah, uh, x and y. Okay, and we are, of course, I missed one assumption here, that this x and y are monotonically increasing function. So when I talk about this one, the En is nothing but the union of all sets En up to n, and En is the largest set among all the previous EMs. And from probability law property, this will be equal to probability of the countable infinite union of ENs, and this we can show is equal to omega. Because if you keep on including one set by one set and it's monotonically increasing to infinity, you can prove that for this will eventually cover the complete set. There is no omega which will be left, because no matter what omega you will take, the x omega y omega maps to a number less than infinity. So you will be able to find one x and yn which is above that number. So from this we can say this is equal to 1. So this moves to limits to 1. Similarly, if x and y both moves to minus infinity, eventually you will the set minus infinity comma x cross minus infinity comma y will not have any outcomes in the pre-image. So the probability would be 0, hence the CDF will also be 0. And of course, monotonicity, if x also increase and y also increase, then y fxy should also increase. So formally, we can say if x is less than x prime and y less than y prime, fxy is less than or equal to fx prime comma y prime. Okay, and how do we prove this? It's very easy. The same way we proved for CDF, you can see that minus infinity comma x prime and minus infinity comma y prime, this is a bigger rectangle, and this rectangle can be broken into 4 parts. One would be minus infinity comma x cross minus infinity comma y, and then this which be this set, and then there will be this set which is between x and x prime and y prime, and then there are 2 more sets which are made such that x is more than x, so the x coordinate is more than x and less than x prime, but y coordinate is less than y. Similarly for the opposite set for x y also. So you can see that because the probability of any rectangle will cannot be less than 0, so you are adding something in fxy to get fx prime y prime, right? So the pre-image of minus infinity comma x prime cross minus infinity comma y prime will of course have more outcomes than the pre-image of minus infinity comma x cross minus infinity comma y. There are some outcomes which maps to a number such that x omega or y omega is more than x and y but less than x prime and y prime. Now we also talk about the marginal distribution. If xy is a, see, fxy is a function of both x and y. If we take limit on x only, then this function will be just a function of y, right? And this is called the marginal distribution of y, and you can show that this will be actually equal to the CDF of y if only one random variable was given, if we did not care about the other random variable. And to prove this, you can see that limit x tends to infinity fxy x comma y is probability that x is less than x and probability that y is less than y. And as you take limit x tends to infinity, this will become probability that x is less than infinity and y is less than or equal to 1. Now x is less than infinity is a redundant condition because of course x will be less than or equal to infinity. It cannot be more than infinity. So we can remove this redundant condition, and the pre-image, if I look at the pre-image of this condition does not matter, because no matter what point we take, x will always map to a number less than minus infinity. So this means the this will be equal to the pre-image of y less than or equal to 1, because this condition is redundant. So what is the probability that y less than or equal to y? It is nothing but the CDF of y. Similarly, if you take y tends into infinity, this will merge to a function of x, which we can show that is also equal to CDF of x. And of course, joint distribution is right continuous from x and y both directions. So if you move from more than x, you will see that as you reach approach x, then because x is always included in the right hand side limit, the probability will not jump. And you will also see the left continuous is different thing. CDF is not left continuous. It will be left continuous only when the both random variables are continuous. And the joint distribution is also continuous. Now let us come back to this example. Let us define random variable x, y, z such that x omega is omega, y omega is 1 minus omega, and z omega is omega. And we saw that they all have the same CDF, but y is not equal to x and while z is equal to x. So how does the joint distribution tells us about this? Okay, it's very clear that if you take the joint distribution of z and x, if you talk about the joint PMF, then you will see that only those values exist where x is equal to z, while here the y and x need to be such that y plus x is equal to 1. Only those points have non-zero probability mass. So if I calculate the CDF of x comma z, I will say that probability is a pre-image made from all omega, set x omega less than x and z omega less than z. So this is x omega is omega and z omega is also omega. So this is probability of all omega such that omega is less than or equal to x and omega is less than or equal to z. Okay, so depending on x and z, this means I can only take omega which are also less than x and less than z. So if x is more than z, then of course I will only worry about the z condition. If z is more than x, I will only worry about the x condition. So basically it is whatever is the minimum of that. So this is this pre-image is equal to omega such that omega is less than minimum of x comma z. So if you plot it for, write it for different values of x and z, you will get this function. If both are less than 0, then of course it will be 0 because there is no omega which maps to this. If x is between 0 to 1 and z is more than x, then this will be a function of x. If x is more than z, this will be a function of z. And if both are more than 1, then of course this will be just equal to 1. Similarly, if I compute the probability of x and y omega, then this will be CDF will be probability that omega is less than or equal to x and 1 minus omega is less than or equal to 1. So this gives you condition that omega should be equal to 1 minus y, omega should be greater than 1 minus y and less than equal to x. So this is the probability of all omega between which are the intersection of 0, 1 and minus 1 comma x, assuming 1 minus y is less than x. And if y minus y is greater than x, then fxy would be 0 because in that case x plus y is less than 1. Also, if x is less than 0 or y greater than 1, then of course there is no x and y omega which can map to this. So this way we got the CDF of this, and we see that this CDF is very different than the CDF of joint CDF of x comma z. So looking at the joint distribution, it is some way easier to know when two random variables are have some correlation or whether they are independent or whether they are equal or not. So now let's talk about the probability density function in the similar way we have done for the probability density function of a single random variable. So here we have a joint CDF and the probability density function, joint probability density function of this two random variables are defined in the following way, that if there exists a function, a two-dimensional function fxy, such that for any Borel set A, so this Borel set is a rectangle or can be any made from two Borel cross product of two Borel one-dimensional Borel sets. So this can be a rectangle or the intersection, countable intersections sorry, countable union of disjoint rectangles. So if you take any such Borel set A, then the probability that x omega y omega belongs to A, or the probability law of this A under xy should be equal, can be computed by just integrating this two-dimensional function on this area A. If this is true for all possible values of A, then we say that the fxy is the density function, probability density function of x comma y, or the PDF of the CDF of xy, or the PDF of the probability measure of xy. Okay, and this has the same interpretation that once you take a very small area of dx comma dx dy area, then the probability that xy belongs to this small area is lie in this small area is equal to the density at this point f x comma y multiplied by the area dx dy. And then once you take a bigger set, then you should be able to divide into smaller sets and take a summation, which is integration in the continuous case. So if I take a equal to minus 20 comma x cross minus 20 comma y, then this probability law will be nothing but this joint CDF. So joint CDF of xy should be equal to the integration of the PDF on the interval minus infinity comma x cross minus infinity comma y, which can be written in a two-dimensional integration where x moves from minus infinity comma x and y moves from minus infinity comma y. Okay, do not confuse this xy with this xy. These are the xy of where I need to calculate the CDF. And these are local variables. So you can replace them by just saying u comma v du dv. This is local variable. So you compute this, and finally you put limit minus 20 comma x and minus 20 comma y for these two variables separately to calculate the value of CDF at these two locations. So this you can just say fxy u comma v du dv, or any local variable you can take. So similarly, if the CDF is continuous, then you can compute the PDF by differentiating the CDF. So it's a two-dimensional integration. So you will differentiate fxy with partially with y and then x, and you will get the CDF of PDF of xy. If x and y are instead discrete random variables, then instead of the PDF, joint PDF, you will talk about the joint PMF, which is nothing but the probability of all omega such that x omega is equal to x and y omega is equal to y. And this can be looked at by, again, looking at the jumps of the staircase CDF. So suppose you want to know for PMF for any x and y, you just try to see is there any jump which is made at x comma y. Okay, so then for any set, if I know the PMF, then for any set A, I can say the probability that that xy belongs to this set A, I will just sum over all the range of x comma y, these random variables, and I will include the probability corresponding to those pair which belongs to A. So if suppose x and y are such that they take four values, 1 comma 1, 1 comma 2, 2 comma 1, and 2 comma 2. And if I take a set A which only has 2 comma 2, so probability law of this set A would be just the probability that x omega is 2 and y omega is also 2. If this set A takes 2 comma 1 and 2 comma 2, then I will add the probability that x is 2, y is 2, and probability that x is 2 and y is 1. Similarly, the PDF can be written equivalently from the PMF by using the impulse function. So there will be two impulses, x minus 1 is x naught and y equal to y naught, and all the you will add for any values of and you will add all the range. So all the impulses at all these pairs which are included in the range of capital X and capital Y. Okay, and you can show that if you integrate this for any set A, you will get the above expression.